Hi, I want to take a look at an example of thermal conduction in an everyday context, trying to heat a relatively largish house with relatively thin walls on an extremely cold day where you set the thermostat incredibly high. So I'm making a lot of assumptions here to directly inflate the numbers, but a lot of our expenditure on energy in the United States and around the world is about modifying and maintaining temperatures. So the house that we're looking at has a front dimension of 10 meters. It's 8 meters deep. It's 2-story, so the roof is about 6.7 meters above the ground, and it goes up to an ultimate height at the crest of the roof of 8.2 meters. Now, for thermal conductivity, the thermal conductivity power, the rate at which energy is leaking through a slab of material, is equal to the thermal conductivity of that material times the cross-sectional area of that object times the temperature difference between the inside and outside divided by the thickness of the material. So I'm going to make some assumptions. I'm going to assume that all of the walls are on average 6 inches thick, which is 0.15 meters. I'm going to assume that they all have roughly the same thermal conductivity, that the internal temperature is uniform all throughout. So if you think about most attics usually have a pretty thick insulating layer in the floor so that inside the attic itself it can actually get and stay relatively cold to try and help minimize conductive loss through that. But let's say, for whatever reason, the attic was designed to be finished. It has about the same thickness roof and about the same thermal conductivity as all of the walls. And let's say that thermal conductivity is about 0.52 watts per meter in Kelvin. So a really hot temperature inside a house is about 80 Fahrenheit. Let's say it's a pretty cold day. It's 20 Fahrenheit outside. That would be a 60 Fahrenheit temperature difference, which is 33 1/3 Celsius or 33 1/3 Kelvin. Now, if I look at the surface area, for the front, I'd have 10 meters times 6.7 meters, so that gives me 67 square meters for the front and back. The sides, I have an 8 meter by 6.7 meter rectangle with an 8 meter by 1.5 meter high triangle, so that's going to give me about 60 square meters on each of the sides. And for the roof, given the height of the roof and the base, the roof would have a length of about 4.3 meters, a base of 10 meters, so we'd be looking about 43 square meters for each side of the roof. So add it all together, that gives us about 340 square meters of total surface area. So the power at which that thermal energy is leaking through that house is 0.52 watts per meter Kelvin times 340 meters squared times 33.3 Kelvin, temperature difference between the inside and outside, divided by that 0.15 meter wall thickness, gives us 39 kilowatts, 39,300 watts of power. Now, if you have a natural gas heater, 1 cubic foot of natural gas will provide about 1.1 million joules worth of energy. So that means that if I divide by 1.1 million joules, I'd be using 0.036 cubic feet of natural gas per second, which works out to be 3,100 cubic feet of natural gas per day, and the unit which you're typically built in is capital MCF. It's not mega cubic feet, it's not a metric unit, it's an old archaic-y Englishy unit for 1,000 cubic feet. So that would be 3.1 billable units of natural gas per day. Now, taking a look at utility rates in Ohio right now, some rates are lower than $2 per 1,000 cubic feet because there's a pretty big energy price war going on in the midst of the economic slowdown of early 2020. It can be as high as $9 per 1,000 cubic feet. So that means that if it's about 20 Fahrenheit outside, a pretty cold winter's day, you have thin walls and you want to keep the thermostat set at 80, it's costing you between $6 and about $28 to $30 a day to heat your house. Thanks for watching.